Hi physicists! So I'm gonna give you some notes on a very important concept in physics called free body diagrams, and it's a way to pictorially model forces. So the very first thing that you need to know is that you represent the object with a dot. So you draw a dot to represent the object. So I like to make a nice big dot like that. And I have kind of a joke. Would you like to see me draw the Statue of Liberty? I'm an artist. All right, I'm gonna draw the Statue of Liberty. Isn't that great? That's a great depiction of the Statue of Liberty. Let's see, what else could I draw? I could draw a T-Rex. There we go. T-Rex. There it is. You know, I could also draw Mr. Trujillo. Here we go, Mr. Trujillo. Although I think the one object that is not just a dot is Mr. Trujillo. Mr. Trujillo is, of course, a bearded dot. Do you like my bearded dot that is Mr. Trujillo? Yeah, definitely Mr. Trujillo. Anyway, I know I'm joking. I hope you know I'm joking. Even on the AP test, represent Mr. Trujillo as a dot, not a bearded dot. So you draw a dot to represent the object, and then you represent forces with arrows. And there's a few notes that go along with that. So if I wanted to put a force, so this is the object, and the dot is the object. And if it has a force on it, this would be the force, that arrow, something like that. And there's a few things that we need to know about these arrows. There's a few rules to them. The first rule is the direction of the force is the direction of the arrow. So clearly there is a force to the right on that object. Second rule is the bigger the arrow, the bigger the force. So let's say I wanted to make a force that was twice as big as this one. I would make the arrow twice as long. Then the last one is kind of weird, but it's just a convention. And the tail end of the arrow must always touch the dot. So the tail end of the arrow must always touch the dot. So what that means is, so you see how up here I drew the tail end of the arrow. So this kind of looks like somebody's pulling, right? But you never, ever, ever, ever draw it like that. Don't. So that would be the tip end touching the dot. So even if something's being pushed, you always have to draw it with the tail on the dot. All right, so that's the rules for drawing free body diagrams. And now I'm going to talk about the types of forces that you could have on a free body diagram. So the first type of force is Fg, and that is the force due to gravity. This is the weight. And you guys know an equation for that Fg equals mass times gravity, or mass times this 10 meters per second squared. The next type of force is a normal force, Fn. And it just means normal because of the word normal means perpendicular. So perpendicular, if this is my cell phone, this marker is perpendicular to my cell phone. And there's a type of force that is, normal forces are always perpendicular to the surface. So this is the force exerted by the surface on an object. And so I think my best example of this is I'm sitting in a chair right now. And I can feel the chair holding me up. I can feel that. And that chair holding me up is exerting a normal force. And that normal force is kind of just because I have weight, right? I have weight, so I'm pushing down on the chair. So the chair must be holding me up. So surfaces hold you up. And so the free body diagram for me sitting in my chair right now would be I have a force, my weight, and I have my normal force, I have my force normal going up, and those should be equal and opposite because I'm not accelerating out of my chair. You don't see me floating out of my chair. I'm also not floating into the surface of the earth, so those two things are equal and opposite. Now I want to caution you guys because the normal force is not always equal to the weight. So a couple examples, if you're skiing, you might be on a hill like that, and you would have a force of gravity going down, but your normal force has to be perpendicular to the surface. And so it would be pointing this way, and it turns out it's not equal to the weight because they're not like pointing directly opposite of each other. And we'll study that a little bit more later. You might also be like, let's say, have you ever pulled your friend on a sled? If you're pulling your friend on a sled, you might be exerting the force of pull up this way, right? And your friend has a normal force, but the fact that you're pulling up a little bit actually like lightens your friend out of the sled. You're pulling up a little bit, and so then your I just labeled that wrong. That should be Fg. Your Fn, your normal force, would become a little less. Similarly, let's say you're pushing down on an object. Pushing down, like let's say you're pushing a shopping cart, kind of down at an angle. Your force of push is down here at an angle. Still has a force of gravity, but if you're pushing down on something, you're kind of grinding the surfaces together. So if you see my coffee cup, and let's say it's on this surface of my cell phone, and I push down on it, I'm kind of grinding the surfaces together, so my normal force actually gets a little bigger. So Fn would get a little bit bigger. So there's some examples of normal forces. Those are actually some examples of free body diagrams, right? That's an example of an object just sitting there at rest in a chair. All right. Hey, I'm doing a notes video right now. Sorry. All right, so let's see, where am I? Then the last type of force I want to talk to you about is the force of friction. So F little f is the force of friction. And the force of friction, there's two types. There is force of kinetic friction. So kinetic friction is normal friction. It's just the object is moving. And then the other one is force of friction static, and this is the object is not moving. So you might ask yourself, how could an object not be moving when it has friction? So I have my water bottle here, and I'm going to push on my water bottle. And I'm pushing on my water bottle, but it's not moving. So the thing that's opposing my push is static friction. And then I could push a little bit harder and get it to move, and now it has kinetic friction. And the force of static friction, I should write this down. So static friction, sorry about that. Static friction, the object is not moving, and the force of static friction is always equal to the force of the push. So the force of static friction gets bigger and bigger and bigger until it is overcome. So as soon as you push hard enough to overcome static friction, that's when the object starts moving. All right, so just want to end with an example here. So my last example is Mr. Trujillo is being rolled in a wheelie chair. So not a wheelchair, but like a office wheelie chair, like what I'm in. All right, so we got to draw Mr. Trujillo. And since he's our one and only object that has something else besides a dot, we've got a little dot beard on him. So we've got Mr. Trujillo. Mr. Trujillo, of course, has a weight. Oh, Mr. Trujillo has much more weight than that. Gravity. Since he's not accelerating up or down out of his chair, he's got a force from the floor. This is called the normal force. And we're going to go ahead and say, I am pushing him. So we've got a force of push, and there's probably a little force of friction, and this would be the kinetic friction opposing him. So there we go. We drew Mr. Trujillo. We drew his weight. We drew the normal force. Those are the first two that I would always draw. I'm pushing him, so we drew a force of the push. And there is friction, and friction always opposes the push. All right, good luck.